50 feet in diameter, 50 tons of wood. No metal gears, no iron axles, no steel reinforcement, just wood. Timber, pegs, and wooden pins holding together a wheel the size of a 5-story building that would spin continuously for decades, generating enough power to run an entire sawmill. A wheel that could take a 2-foot diameter log and reduce it to boards in minutes. A wheel built by hand, by men using axes and adzes, assembled on-site with techniques that hadn't changed since the Middle Ages, and there were thousands of them. Across America, from New England to the Pacific Northwest, massive wooden water wheels turned the lumber that built the country. They were engineering marvels that most people have never heard of, and they're almost all gone now. This was America in the 1800s, and the country was being built from wood. Houses, ships, bridges, factories, railroads, all of it required lumber. Lots of lumber. And producing lumber required power. Before steam engines became common, before electricity, before internal combustion, the only reliable source of mechanical power for industry was falling water. Water captured by a wheel. A wheel that had to be large enough to generate serious power, but also strong enough to withstand constant stress, built from a material that could be worked with hand tools, but wouldn't rot or break under load. The answer was wood. Massive wooden wheels. Some of the largest wooden structures ever built, turning day and night, powering the saws that cut America's forests into lumber. Could you really build a 50-foot wheel entirely from wood that would be strong enough to power industrial machinery? Could you design a wooden structure that would last for decades under constant load and exposure to water? And could you build it on-site in the wilderness using only hand tools and techniques that had been developed centuries earlier? The answer is yes. The evidence is scattered across the country in the form of massive axle stones, mounting hardware, and occasional preserved wheels that show what American millwrights accomplished. Before we get to the wheels themselves, you need to understand what they were powering and why they had to be so large. Because these weren't decorative watermill wheels like you see in paintings. These were industrial machines designed to generate serious power for heavy work. A sawmill in the 1800s required tremendous amounts of power to operate. The main saw, typically a vertical blade called an upright saw or later a circular saw, had to cut through logs that could be several feet in diameter. The blade moved through dense wood under constant resistance. That required power. The log carriage, the mechanism that held the log and fed it through the saw, had to move smoothly and precisely. That required power. The various auxiliary equipment, conveyors, planers, edgers, all required power. A medium-sized sawmill might need 20 to 30 horsepower to operate effectively. A large mill might need 50 horsepower or more. To understand what this meant in practical terms, consider the main saw of a typical sawmill. An upright saw might have a blade 10 feet long and 8 inches wide. This blade moved up and down through the log in a reciprocating motion, and making anywhere from 200 to 400 strokes per minute depending on the wood being cut. Each stroke required force to overcome the resistance of cutting through wood. The power requirement wasn't constant. It would spike when the blade was actively cutting and drop during the return stroke. The water wheel and power transmission system had to be designed to smooth out these variations and provide consistent power. The circular saws that became common in the 1850s and later required different power characteristics. A circular saw blade might be 6 feet in diameter, spinning at several hundred revolutions per minute, with teeth continuously engaging the wood. The power demand was more constant than with an upright saw, but the total power requirement was higher. A large circular saw cutting through a 3-foot diameter log might require 40 or 50 horsepower at peak load. The formula for power from a water wheel is relatively simple. Power equals force times velocity. The force comes from the weight of water acting on the wheel. The velocity is how fast the wheel turns. To generate more power, you need more force, which means more water acting on a larger wheel, or higher velocity, which means faster water flow. But there's a practical limit to how fast you can make water flow, and many mill sites didn't have access to high-velocity water. The solution was to make the wheels larger, much larger. The engineering calculations behind water wheel design were sophisticated, despite the lack of formal engineering training among most millwrights. A millwright needed to know the water flow rate of the stream in cubic feet per minute. They needed to know the vertical drop available, the head. From these numbers, they could calculate theoretical power available. Then they had to design a wheel that would capture as much of that theoretical power as possible while being buildable and durable. The efficiency of a well-designed overshot water wheel could reach 70 to 85% under ideal conditions. That means if the theoretical power available from the falling water was 60 horsepower, a good wheel might deliver 50 horsepower to the machinery. This was actually better efficiency than early steam engines, which often operated at 20 to 30% efficiency. The water wheel's main limitation wasn't efficiency, but dependence on consistent water flow. The typical water wheel that powered a sawmill was between 30 and 50 feet in diameter. Some were larger. The Great Laxey wheel on the Isle of Man, though not a sawmill wheel, was 72 feet in diameter and was built using similar techniques. A 50-foot wheel could generate 40 to 50 horsepower under good water conditions. That's equivalent to 50 horses working continuously, or more power than many small steam engines of the era. But building a wooden wheel that large presented enormous engineering challenges. Wood is strong in some ways and weak in others. It handles compression well, but can fail in tension. It's relatively light compared to its strength, which is good for a structure that has to rotate, but it absorbs water, which adds weight and can lead to rot. And perhaps most importantly, wood isn't uniform. On every piece of timber has grain, knots, variations in density. Building a large wooden wheel meant understanding these properties and designing around them. The construction of a major water wheel was a specialized craft practiced by millwrights, skilled carpenters who understood both structural engineering and power transmission. A millwright could look at a water source, calculate the available power, and design a wheel that would extract maximum energy while being buildable with available materials and lasting for years under constant use. The basic design of an overshot water wheel, the type most commonly used for sawmills, consisted of several components. At the center was the axle, a massive wooden beam that might be 24 inches square and stretch 40 feet from one bearing to the other. This axle had to be made from a single tree, usually oak or another hardwood known for strength. Finding a tree large enough to produce an axle for a 50-foot wheel wasn't easy. The tree had to be straight, free of major defects, and large enough when squared to maintain structural integrity. Radiating out from the axle were the arms, wooden beams that extended to the rim of the wheel. These arms, also called spokes, were mortised into the axle using carefully cut joints that distributed the load. A large wheel might have 8 to 12 arms. Each arm was a single piece of timber, typically 12 to 18 inches square, extending 25 feet or more from the axle to the rim. The precision required to cut these mortises and fit the arms was extraordinary, and the joints had to be tight enough to transmit rotational force without slippage, but not so tight that seasonal expansion and contraction of the wood would split the axle. The rim of the wheel consisted of curved segments called felloes, similar to barrel staves but much larger. These felloes were shaped to form a circle and were connected to the ends of the arms. The shaping of felloes for a wheel that might be 50 feet in circumference required significant skill. The wood had to be cut or steamed to create the curve, then fitted precisely so the rim would be round. An out-of-round wheel would vibrate and eventually shake itself apart. Attached to the outside of the rim were the buckets or paddles, the surfaces that actually caught the water. In an overshot wheel, these were bucket-shaped compartments that would fill with water at the top of the wheel. The weight of the water in the buckets would cause that side of the wheel to be heavier, creating rotation. As the wheel turned, the buckets would dump their water at the bottom and rise back up empty to be filled again. The buckets had to be designed to hold water long enough to extract energy, but release it before it started working against the rotation. Every component of the wheel was connected using wooden joinery, mortise and tenon joints, wooden pegs called trunnels, tree nails, driven through drilled holes, wedges that would swell when wet, tightening the joints, No nails, no bolts, no metal fasteners in the main structure. Metal was used for the bearing surfaces and for the connection to the power transmission system. But the wheel itself was wood held together with wood. The construction process for a major water wheel could take months. First, the timber had to be selected and prepared. The millwright would go into the forest, mark suitable trees, and supervise the cutting and shaping. The axle timber had to be particularly perfect. Any defect could lead to failure under load. The arms and rim pieces could tolerate minor flaws, but still had to be high-quality wood. Finding the right timber was itself a major undertaking. For a 50-foot water wheel with a 24-inch square axle, you needed a tree that was at least 36 inches in diameter at breast height and straight for at least 40 feet. Such trees weren't common even in virgin forest. The millwright would search for days or weeks to find suitable candidates. Once found, the tree had to be felled, transported to the mill site, and squared. The squaring was done with broad axes, wide-bladed axes designed for smoothing flat surfaces. A team of hewers would work on an axle timber for weeks, gradually transforming a round log into a square beam with remarkably flat surfaces. The precision achieved with these hand tools was impressive. A good hewer could create surfaces flat to within a quarter inch over 40 feet of length. They'd use chalk lines to mark the desired surfaces, then chip away the wood methodically. The work required both strength and finesse. Hit too hard, and you'd tear the wood grain, creating weakness. Hit too lightly, and progress would be impossibly slow. The master hewers were highly valued workers who could demand premium wages. The arms required similar care but different timber, and each arm needed to be from a single tree, large enough to provide a 12 to 18-inch square beam 25 feet long. That's a substantial tree, and you needed 8 to 12 of them. For a remote mill site, this might mean cutting timber from the surrounding forest. But for an established mill replacing an old wheel, the timber might need to be brought in from miles away because the nearby forest had been logged out. The shaping was done with hand tools. Axes to rough out the shape, adzes to smooth surfaces, hand augers to drill holes for trunnels, chisels to cut mortises. All of this work was done by eye and experience. The millwright might use simple measuring tools, straight edges, squares, dividers, but there were no precision instruments. The accuracy came from skilled craftsmen who'd been doing this work for years. And the mortise cutting for the arm joints was particularly demanding work. Each mortise had to be cut into the axle to receive the tenon at the base of an arm. The mortises had to be precisely positioned around the axle to balance the wheel. They had to be cut to exact depth and width. Too loose and the joint would fail. Too tight and the wood might split when the arm was driven in. A master millwright would spend days laying out and cutting these mortises, checking and rechecking measurements, test-fitting components. The assembly was a community event in many cases. Building a large water wheel required more workers than a single mill employed. Neighboring mills would send workers to help. Local farmers would come to assist. The work was hard and dangerous. But there was a shared understanding that everyone benefited from having functional mills in the area. The mill owner would typically provide food and drink for the assembly crew, a practice that turned water wheel raising into a social occasion. The first step in assembly was positioning the axle. This massive beam, weighing several tons, had to be lifted into place on its bearing blocks. The technique was similar to raising a ship's mast. A wooden crane called a gin pole would be erected near the work site. Rope would be rigged through pulleys. A team of workers, sometimes dozens of men, would pull on the ropes, while others guided the axle using long poles. Getting the axle precisely level and aligned took hours of careful work. If the axle wasn't perfectly aligned, the wheel would wobble during operation and quickly destroy itself. But once the axle was in place and secured, the arms would be fitted. This had to be done in sequence, balancing the wheel as you went. You couldn't install all the arms on one side first. The uneven weight would stress the axle mounting. The millwright would direct workers to install arms in a pattern, constantly checking balance. Each arm had to be driven into its mortise using heavy wooden mallets and wedges, then locked in place with trunnels driven through pre-drilled holes. There's a documented account from a mill in Vermont in 1842 that describes the raising of a 45-foot water wheel. The account, written by a visitor to the mill, details how the assembly took 3 weeks and involved over 40 workers at its peak. The visitor describes the precision required. The millwright directed every action with extraordinary care. Each arm had to fit perfectly, each trunnel driven exactly flush, each rim section curved to match its neighbors. The work proceeded slowly, but with evident skill. These men were building not merely a machine, but a work of craftsmanship that would serve for decades. Once all the components were prepared, the wheel had to be assembled. This was typically done on site, which meant building a massive wooden structure in whatever location the mill was situated, often in remote wilderness. The assembly required considerable manpower. The axle alone might weigh several tons. Moving it into position, getting it precisely level and aligned, required block and tackle systems and crews of workers. The arms would be fitted into the axle one at a time, each joint carefully checked for fit and then locked in place with trunnels. And once all the arms were in place, the felloes would be attached to create the rim. Then the buckets would be added. The entire structure had to be balanced. Uneven weight distribution would cause the wheel to wobble or vibrate during operation. The bearing system for the axle was critical. The axle had to rotate freely while supporting the weight of the wheel plus the weight of water in the buckets. Some wheels had wooden bearings, hardwood blocks lined with softer wood that acted as bushings. But most large wheels used iron-bearing plates or even roller bearings for the critical contact points. These metal components were some of the few metal parts in the system. The power from the wheel was transmitted to the sawmill through a series of wooden gears and shafts. The axle of the wheel would have a large wooden gear attached to it, called the pit wheel because it was usually located in a pit below ground level. This pit wheel would mesh with a smaller gear called a wallower, which was attached to a vertical shaft. That vertical shaft would rise up into the mill and connect to the main power distribution system. These wooden gears were themselves impressive pieces of engineering. A pit wheel for a large water wheel might be 12 to 15 feet in diameter with dozens of wooden teeth. The teeth, called cogs, were made from hardwood, often applewood or hornbeam, chosen for their ability to withstand impact and wear. The cogs were inserted into the rim of the gear and could be replaced individually as they wore out. The mesh between the wooden gears had to be precise. Too tight and the friction would be excessive, causing heat and wear. Too loose and the gears would clatter and eventually damage themselves. Millwrights would adjust the mesh by moving the vertical shaft slightly, using adjustable bearings that allowed fine-tuning. The maintenance of a large wooden water wheel was constant and demanding. Wood exposed to water will eventually rot. The buckets, which were constantly wet, had to be replaced every few years. The felloes, which were alternately wet and dry as the wheel rotated, would deteriorate faster than the internal structure. Even the axle, protected somewhat by being mostly dry, would eventually develop checks and cracks. A mill would typically employ a full-time millwright just to maintain the wheel and power system. This person would inspect the wheel regularly, looking for cracks, loose joints, or worn components. They'd replace buckets and felloes as needed. They'd adjust bearings, tighten trunnels, check the gears. The work was skilled and necessary. A major failure of the water wheel would shut down the entire mill. The seasonal cycle of maintenance was predictable. Spring, with heavy runoff, put maximum stress on the wheel. The increased water volume meant more weight in the buckets, more force on the arms and axle. The millwright would inspect carefully after spring floods, looking for damage. Summer, with lower water flow, was typically when major maintenance was scheduled. The reduced water meant the mill might run at partial capacity or shut down entirely, giving workers time to replace worn components. Fall presented different challenges. Leaves and debris would accumulate in the water, so clogging the mill race and getting caught in the buckets. Constant cleaning was necessary. Winter was perhaps most difficult. In northern climates, ice would form on the wheel. The weight of ice could be substantial. Thick ice accumulation on a 50-foot wheel could add tons of weight. Worse, ice could jam the wheel entirely, preventing rotation. Mill workers would have to chip ice off manually, or in severe cases, drain the mill race entirely until temperatures rose enough to melt the ice naturally. Specific mills with notable water wheels included the Ames Sawmill in Massachusetts, which operated a 52-foot water wheel from 1831 to 1889. This wheel was documented as generating approximately 45 horsepower and powering a sawmill that processed over 2 million board feet of lumber annually during its peak years. The wheel was replaced twice during its operation, once in 1855 when the original axle developed cracks, and again in 1873 when the entire structure was rebuilt to incorporate improvements in bucket design. The mill records, preserved in the Ames Historical Collection, show that maintenance costs for the water wheel averaged about $400 per year, roughly $12,000 in modern currency. The Collins Axe Company in Collinsville, Connecticut, operated a complex of water wheels that powered not just sawmills but also forges and grinding operations. The largest wheel, built in 1843, was 48 feet in diameter and powered the main sawmill. This wheel was notable for its iron reinforcement, unusual for the era, which consisted of iron bands around the rim to prevent the felloes from separating. The reinforcement added significant cost, but extended the wheel's operational life to over 50 years. The Collins wheel didn't shut down until 1906, when the company finally converted to electric power. In the Pacific Northwest, the mills operated water wheels under different conditions than their eastern counterparts. The consistent rainfall meant year-round water flow, reducing the seasonal variation problems. But the massive logs, Douglas fir, and cedar trees that could be 6 feet in diameter required more power than eastern mills. The Stimson Mill in Ballard, Washington, operated what was reportedly one of the largest sawmill water wheels in America, measuring 54 feet in diameter and built entirely from old-growth fir. This wheel powered a two-saw operation that could process logs up to 8 feet in diameter. The wheel operated from 1889 to 1903 when it was replaced by a steam power plant. The danger of working around these massive wheels was significant. The wheel was constantly rotating, usually at a speed of about 5 to 10 revolutions per minute. That might not sound fast, but for a 50-foot wheel, the rim is moving at about 15 miles per hour. If you got caught in the wheel or the gears, you'd be crushed. There are accounts of workers being killed when they got too close to the rotating machinery. One documented incident from 1847 in Maine involved a millwright named Samuel Porter, who was working on the bearings of a water wheel while it was shut down. Someone upstream opened the water gate without realizing Porter was working on the wheel. Water hit the buckets, the wheel began to rotate, and Porter was caught between the axle and the bearing housing. He was crushed before anyone could reach him. The mill shut down for 2 days while his body was recovered and a replacement bearing was installed. Then operations resumed. Another incident from 1852 in Pennsylvania killed a young worker named Thomas McGraw who was cleaning debris from the pit wheel, the large wooden gear at the base of the water wheel. McGraw slipped, and his hand was caught in the mesh between the pit wheel and the wallower. The gears pulled his arm in and tore it off at the shoulder. He bled to death before medical help could arrive. He was 17 years old. The mill owner paid for his burial and gave his mother $20. There was no workers' compensation, no liability, just $20 and a grave. There was also the case of William Hendricks, a millwright at a sawmill in New Hampshire, who was killed in 1861 while replacing a damaged arm on a water wheel. The wheel had been partially disassembled, with some arms removed. Hendricks was working to install a new arm when the remaining arms became unbalanced, causing the wheel to rotate unexpectedly. The massive axle shifted in its bearings, and Hendricks was pinned against a support beam. The other workers managed to stop the wheel and free him, but his injuries were too severe. He died that night in the mill owner's house, attended by his wife and the local doctor who could do nothing for him. Hendricks was 34 years old and left behind a wife and 4 children. In 1868, a catastrophic failure at a mill in upstate New York killed 3 workers and destroyed the entire sawmill building. The axle of a 40-foot water wheel developed a crack that went unnoticed during routine inspections. Under load, the crack propagated until the axle snapped completely. When the axle broke, the wheel came apart violently. The arms, no longer held by the axle, were thrown outward by centrifugal force. The pit wheel disintegrated. Debris from the wheel crashed through the mill building. 3 workers inside the mill were killed by flying timber and collapsing structure. The mill never rebuilt. The owner declared bankruptcy, and the property was sold for salvage. The business economics of Waterwheels shaped the entire sawmill industry in the 1800s. A mill's profitability depended on having reliable power at reasonable cost. A well-designed water wheel represented a capital investment that would pay for itself through years of operation. But the economics were more complex than just initial cost versus operating savings. Water rights were often the most valuable asset a mill owned. The legal right to divert water from a stream and use it for power generation could be worth more than the mill building itself. Mills would go to court to protect their water rights or to dispute upstream users who diverted water and reduced flow. There are documented cases of mill owners purchasing land miles upstream just to control water sources and prevent competitors from diverting flow. The seasonal variation in water flow created business challenges that affected mill operations and profitability. In regions with distinct dry seasons, mills might only operate 6 or 8 months per year. During low water periods, the water wheel couldn't generate enough power to run the full mill capacity, so production dropped. Mill owners had to accumulate inventory during high-flow months and manage cash flow carefully to survive low-flow periods. Some mills would shut down entirely during summer drought, sending workers home without pay until fall rains resumed. The competition between water-powered mills and steam-powered mills was shaped by geographic and economic factors. In areas with reliable water flow year-round, water wheel mills could compete effectively because they had no fuel costs. In areas with seasonal water variation, steam mills had an advantage despite higher operating costs because they could produce consistently year-round. By the 1880s, the pattern was clear. New mills in areas with marginal water resources were being built with steam power, while areas with good water continued to use water wheels. The capital required to build a complete water-powered sawmill in 1850 was substantial. The water wheel might cost $2,000 to $3,000. The dam and mill race system might cost another $1,000 to $2,000. The mill building and sawing equipment might cost $3,000 to $5,000. Total investment could easily reach $8,000 to $10,000. Equivalent to $250,000 today. This was beyond the means of individual workers. Mill ownership required either accumulated capital or access to loans and investors. The social structure of mill towns reflected this economic reality. The mill owner was typically the wealthiest person in the community. The millwright and skilled workers were middle class, earning decent wages but unlikely to ever accumulate enough capital to own a mill themselves. The laborers who cut trees, hauled logs, and stacked lumber were working class, living paycheck to paycheck. The water wheel, as the power source for the entire operation, was literally at the center of this economic system. The scale of water wheel use in America is difficult to comprehend. Every sawmill, grist mill, textile mill, and industrial operation that needed power and had access to flowing water used water wheels. In the mid-1800s, there were probably 10,000 or more industrial water wheels operating in the United States. Most were smaller than the massive sawmill wheels, but hundreds were in the 40 to 50-foot range. These wheels represented enormous capital investment. A large wooden water wheel might cost $2,000 to $3,000 to build in 1850, equivalent to $60,000 to $90,000 today. That doesn't include the cost of the dam and water management system or the mill building itself. For a small operator, the water wheel might represent half the total capital investment in the mill. But the investment paid off. A good water wheel could operate for 20 to 30 years with proper maintenance, and the fuel was free. Unlike steam engines, which required constant supplies of coal or wood, the water wheel just needed flowing water. In areas with reliable water flow year-round, the water wheel was essentially a free energy source that required only maintenance labor. The decline of the wooden water wheel came gradually with the rise of steam power and later electricity. So steam engines offered advantages that water wheels couldn't match. A steam engine could be located anywhere, not just where water flowed. It could generate consistent power regardless of seasonal water flow variations. And it could be scaled more easily. You could add more engines or bigger engines without having to redesign the entire power system. By the 1880s, new sawmills were increasingly being built with steam power, but many existing mills continued to use their water wheels. The wheels were already paid for, they were producing adequate power, and replacing them with steam would require significant capital investment. Some mills operated hybrid systems, using the water wheel when water was available and supplementing with steam during low water periods. The final death blow for water wheels came in the early 1900s with rural electrification. Electric motors were cleaner, more efficient, and required minimal maintenance compared to either water wheels or steam engines. Mills could replace a 50-foot water wheel and its complex system of gears and shafts with a few electric motors mounted directly on the machinery. The conversion was dramatic and quick. By 1920, most of the large wooden water wheels had been abandoned. The mills either converted to electric power or shut down entirely. The water wheels were left to rot. Some were dismantled for salvage timber. Most were just abandoned in place. The wooden components deteriorated quickly once they were no longer maintained. Within a decade of abandonment, a water wheel would be unrecognizable ruins. Today, very few original large wooden water wheels survive. There are some preserved as historical exhibits at museum sites. The Bale Grist Mill in Napa Valley, California, has a 36-foot water wheel rebuilt using original techniques. The Mingus Mill in North Carolina has a working water wheel. These are smaller than the giants that powered major sawmills, but they demonstrate the engineering and craftsmanship. The preserved wheels that do exist are invaluable for understanding how these machines actually worked. At the Bale Mill, visitors can see the water wheel in operation, watch water fill the buckets, observe the power transmission through wooden gears. The mill staff explains the engineering principles and demonstrates the maintenance techniques that would have been required. It's one thing to read about a wooden water wheel. It's entirely different to stand next to one while it's operating, to hear the splash of water and the creak of timber, to feel the ground vibrate slightly from the rotation of tons of wood. Other preserved examples exist in various states of completeness. The Hagley Museum in Delaware has water wheel components from the DuPont powder mills. The Slater Mill in Rhode Island preserves the water wheel system that powered early American textile manufacturing. The Old Stone Mill in Delta, Pennsylvania, maintains a working wheel. These scattered examples represent the survivors from thousands of wheels that once operated. What remains of most of the sawmill water wheels are the foundations, stone mounting blocks, mill race channels, dam remnants. If you know where to look in the forests of New England, the Pacific Northwest, or the Appalachians, you can find these ruins. A massive stone block with iron mounting hardware still in place, sitting beside an overgrown stream bed. That stone held the bearing for a water wheel that might have been 50 feet in diameter. The wheel is gone, the mill is gone, but the stone remains, a monument to engineering and craftsmanship. Hikers occasionally stumble across these ruins without realizing what they're seeing. A large stone block in the middle of the forest, worn smooth by weather, might look like a natural formation. But if you look closely, you'll see the precision of the cut surfaces, the carefully drilled holes for mounting bolts, sometimes the worn groove where an iron bearing plate rested. These stones were quarried, shaped, and transported to remote locations specifically to support water wheels. Finding one is like discovering the foundation of a cathedral that the forest has reclaimed. The mill race channels are often more obvious. These are the artificial waterways that directed water to the wheel. Even decades after abandonment, the straight cuts through terrain, the stone-lined channels, the remains of wooden gates and controls are visible. Some mill races are still carrying water, now serving as drainage channels or natural streams that have adopted the artificial course. Walking along an old mill race, you can trace it upstream to where the dam once stood, then downstream to where the mill building was located. The geography tells the story of industrial operations that existed in now wild forests. The wooden water wheel represents something important about American industrial history. These were high-performance machines built with low technology. The millwrights who designed and built them didn't have engineering degrees. They had experience, tradition, and an intuitive understanding of materials and forces. They built machines that generated tens of horsepower using only wood and water, machines that operated reliably for decades, machines that powered the industrial economy of a growing nation. The human skill required to build these wheels was extraordinary. A millwright had to understand structural engineering, fluid dynamics, power transmission, and materials science, all without formal training in any of these fields. They learned by apprenticeship, working under experienced millwrights, slowly absorbing the knowledge of generations. They could look at a stream and calculate the power available. They could design a wheel to extract that power efficiently. They could build the wheel with hand tools and wooden joinery that would hold up under stress. That's engineering at a level that deserves respect. The workers who built and maintained these wheels were often anonymous. We know some names from accident reports and business records, but most of the men who cut the timber, shaped the components, assembled the wheels, and maintained them year after year left no records. They were laborers and craftsmen whose work was essential but not considered worthy of documentation. These men worked with hand tools and muscle power to create structures that modern engineers would struggle to replicate. Try to imagine shaping a 25-foot oak beam into a precisely dimensioned wheel arm using only an axe and adze. Try to imagine drilling a 2-inch hole through that beam, perfectly straight, using a hand auger. Try to imagine lifting a multi-ton axle into position using only rope and wooden poles. That was the reality of water wheel construction. It was hard, skilled, dangerous work. The wages for this work were modest. A master millwright in the 1850s might make $2 to $3 a day. Good money for the time, but not exceptional. The laborers who did the heavy work of moving timber and assembling components made less, perhaps $1 to $1.50 per day. For comparison, a skilled industrial worker in a factory might make similar wages with less demanding work. The men who built water wheels did it because they had the skills, because they took pride in the work, or because it was the best job available in their area. There's a particular poignancy to the fact that these massive structures are almost completely gone. Wooden water wheels were designed to be temporary in a sense. They were built to last 20 or 30 years, not centuries. But they represented such enormous investments of skill and labor that it's hard to accept their complete disappearance. A 50-foot water wheel built by hand from carefully selected timber, assembled with perfect joinery, balanced and tuned to generate maximum power. That's a work of engineering and art. And almost all of them are gone, rotted away, leaving only stones and rusted iron to mark where they once stood. The few preserved wheels that do exist are valuable teaching tools. They show modern people what could be accomplished with simple technology and high skill. They demonstrate that engineering isn't just about advanced materials and computer modeling. Sometimes it's about understanding your materials deeply, designing within their limitations, and building with care and precision. If you ever get the chance to see a working wooden water wheel, take it. Watch how the water fills the buckets. Watch how the weight creates rotation. Listen to the sound, the splash of water, the creak of wooden joints under load, the mesh of wooden gears. Think about the fact that this is how America was powered in the 1800s. This is what generated the energy that cut the lumber, ground the grain, and powered the machinery that built the country. And think about the millwrights who designed these wheels, the workers who built them, the maintainers who kept them running. Think about Samuel Porter, killed when a water wheel started unexpectedly. Think about Thomas McGraw, 17 years old, pulled into wooden gears. Think about the hundreds of anonymous workers who spent their lives building and maintaining these machines. They created infrastructure that made industrial development possible. They built it with wood and skill and hard labor, and they're almost completely forgotten. The wooden water wheels that powered America's sawmills were engineering marvels. 50-ton machines built entirely from wood, operating reliably for decades, generating the power that cut the forests into lumber. They were designed by millwrights who learned their craft through apprenticeship, built by workers using hand tools, maintained by skilled mechanics, who understood the quirks and requirements of massive wooden machines. They were fundamental to industrial development in the 1800s. And they're gone now, leaving only stones and memories and the occasional preserved wheel to show what was once common across America.